Hello and welcome to our fourth video, our fourth inquiry activity, and we're going to continue our discussion about significant digits. Specifically, we're going to be looking at whether a zero in a measurement is significant or not. In other words, is it part of the measurement or is it just a placeholder? So join me and let's look some more at significant figures or significant digits, and we're going to focus on zeros today. Okay, so significant zeros, it says here which zeros are significant in a measurement and which are simply just important. In other words, they're there because they need to be a part of the number, but they're just taking up a particular placeholder, so that all the other digits are in the correct location. When working with measurements, it's important to know which digits in the measurement are significant and which are not. Remember, when we're talking about significant digits, we're talking about those that are part of the actual precision of the instrument that you used. You are allowed to measure with certainty, and then one last digit is going to be an estimation. Non-zero, so any digit 1, 2, 3, 4, 5, 6, 7, 8, or 9 are always significant. You're never going to have a problem there. If you see a digit in your measurement other than 0, it's always going to be significant. However, the zeros can be tricky. Some are significant and others are not. This activity, we're going to be looking at how you determine whether a zero is significant or not. And we're going to be learning some rules that are going to apply, and you can use every single time to determine whether a zero is a significant digit in your measurement. Here's model 1, and you're going to be looking at masses of rocks. In sample A, you have a rock. This is the same rock here, by the way, on all 4 of these different scales, but you'll notice the measurement is different. So for this rock that you just moved from scale to scale or balance to balance, you have initially a measurement of 100 grams, and then 140, and then 143, and then 143.0, depending on which of the balances you used. Same thing here with sample rock B. Same rock on all 4 of the balances. Here it's 200, then 180, 177, and 177.1. Again, depending on which of those balances you chose to place the rock on. Alright, let's look at our questions here. As they're going to build, we're going to start with some simple observations, and then eventually we're going to get to these rules that I mentioned that are going to help you determine whether a zero is significant or not. For each balance in Model 1, circle the phrase below that best describes how closely the mass can be determined with that balance. So we're going to look at all 4 of these balances, and if we look at the econobalance, you'll notice that the econobalance, the measurement is to the nearest 100, to the nearest 100 grams. So you can only use this econobalance, and your estimate or your measurement is going to be to the nearest 100 grams. The good balance, you'll notice that you have measurements of 180 here and 140 here, so that is going to the nearest 10 grams. The balance pro, you have digits here in the units place or ones place, so that is going to the nearest 1 gram. And then for the exacto balance, you've got tenths of a gram, and that means it is estimated to the nearest tenth of a gram. Okay? Which of the 4 balances in Model 1 is the best quality instrument? Well, all of them are useful, have their place in measuring a mass, but the best quality instrument is going to be the exacto. The exacto is going to give you the most digits for any of the measurements. So you're going to get here 4 significant digits. It is taking your measurement out to the nearest tenth of a gram. Okay? Moving on to question number 3. Notice it says rock C is placed on the econobalance and the balance reads 200 grams. Does rock C have a mass larger, smaller, or the same as sample A, or is it impossible to tell? Explain your reasoning. So in this case, we're looking at rock C is placed on the econobalance and the balance reads 200. And we're asked, is it have a greater mass than rock A? Okay? Does it have a larger, smaller, or same as rock A? Well, if it's 200, rock A only came in at 100. So even just using the econobalance, you should be able to tell that rock C is going to have a larger mass than rock A. Okay? Does rock C have a mass larger, smaller, or the same as rock B? Or is it impossible to tell? So in this case, you're not quite sure, because in rock B, it also measured 200. Now, the econobalance is not as precise. So you'll notice that as we use the more and more precise instrument there, you're going to get a more detailed, more accurate measurement. But if you're using the econobalance and you measure rock C at 200 and rock B also came in at 200 on the econobalance, you don't know which one is the heavier one. You don't know if it's rounding off to 200 and it really is 183.6, or it's rounding off to 200 and it's really 201.5. So in this case, it's not precise enough to determine which one is larger. So in this case, it is impossible to determine. The mass of rock C is then measured using the other three balances. Remember, up here we were just using the econobalance. Now it says the other three balances. The results are shown below. And this is for a third rock that we're going to call rock C. Here's the econobalance. Remember, it was 200 as we mentioned in the previous question. Now the good balance brings it in at 180, and then the balance pro at 177, and the exacto at 177.0. Let's just peek up here just for a second. You'll notice the difference here between now rock B and rock C. Here, with the exacto balance is 177.1, and now the rock C is 177.0. Just pointing that out. We'll probably be using that in a little bit. Based on this additional information, does rock C have a mass larger, smaller, or the same as rock B, or is it impossible to tell? In this case, we are able to tell because in the exacto balance, it came in, meaning rock B came in at 1/10 of a gram greater. So in this case, B is going to have a larger mass than C, because 177.1 is greater than 177.0. Okay? Now keep in mind though that this last digit, the 0.1 here and the 0.0, those are your estimates. So the balance, your instrument is estimating that final digit as well. And sometimes when you use a balance, that last digit will fluctuate. You'll see it kind of switching back and forth, and back and forth until it kind of settles on 1, because it is getting that last digit as an estimation. So even though the balance brings the rock B in at 1/10 of a gram higher, it's so close, and we keep in mind that that last digit is really an estimation. Okay? So there may be some discrepancy there. It may be actually not as accurate or not as precise to determine whether B is actually greater than C. Alright, so it might be a little more difficult to tell than we think. Alright, and then if we go down here, explain why the 0 in exacto balance reading provides important information about the mass of rock C, but the 0 in the good balance reading does not. So let's look up here. We're looking at the exacto compared to the good. So this right here, if you have a 0 on your exacto, that last digit is part of the significant measurements, the significant digits in your measurement. That last 0 is your estimated digit. But over here, this 0 is not significant. It's not actually part of your measurement for this balance. It's the 4 that is the estimated digit in this case. That 0 is just there because it's got to push the 1 and the 4 to the correct location to make it 140. But the 0 in this measurement here is not significant. It is not a sig fig, as we say. But here, this 0 is. That 0 is part of the significant figures or the significant digits. So that's the difference in between those two balances. Alright, so for the good balance, the 0 is not a significant figure. It is not a significant figure. But for the exacto, the 0 is a sig fig. Okay? So that's important to determine, and we'll be looking at this a little bit more as we move through. Alright, Model 2. Model 2, again, is going to give you some rocks or pebbles, and they are placed on different balances. And again, you can notice that dependent on how precise that instrument is, it's going to measure it to the nearest gram, nearest hundredth of a gram, or nearest thousandth of a gram. And we have pebble A or pebble B on all of these. For each balance in Model 2, write a phrase to describe how closely the mass of an object can be determined using that balance. The first one is done for you. So, similar to what we did with Model 1, the balance pro here is estimated to the nearest 1 gram, because you'll notice it doesn't go past the 0. So it could be, 0.0 something, but it's rounding it to the nearest 1 gram, so it has to just round down to 0. The centibalance, appropriately called because centi means hundredth, and so it is measuring to the nearest hundredth of a gram. And so this is going to estimate to the nearest hundredth of a gram. And then you've got the super balance, super duper balance, and it is measuring to the nearest thousandth of a gram, going out 3 decimal places to the right of the decimal point. And so that is going to go to the nearest thousandth of a gram. Pebble A and Pebble B both have a mass of 0 grams on the Balance Pro in Model 2. Do these pebbles really have no mass? Well, no, of course not. No, they do not. It's just that it is rounding off to 0 because it is not a half a gram or bigger. If it was a half a gram or larger, it would round up to 1. But it is rounding down. It is rounding down to 0. Okay? It's just that it's not precise enough. It's not sensitive enough to measure the mass past a unit, past the nearest gram. Number 7 here. Which balance is sensitive enough to determine if Pebble A has a mass larger or smaller than Pebble B? So let's compare here at this place right here where we put the 2 different pebbles, Pebble A and Pebble B, on the Balance Pro. They look like they have the same mass. They're both 0. Well, we know they're not 0. It's just that it's rounding off to 0. In the centi balance, they both have the same mass. It's not until you get to the super balance, which is rounding off to the nearest thousandth of a gram, that you see there is actually a distinction, because 0.016 rounds off to 0.02 and 0.020 rounds to 0.02. But now when we get to a more precise instrument, we actually see there is a difference between the 2 measurements. So it's the super balance that makes the distinction, okay? The super one. The mass reading of Pebble B from the super balance is right there, 0.020. This value is very close, but different than the mass reading for Pebble A on that same balance. 0.020 compared to 0.016. Determine which of the 3 zeros in the mass reading for Pebble B is the most significant in terms of determining whether Pebble B has a different mass than Pebble A, and circle the 0 below. So, What they're saying is this has a measurement, pebble A, of 0.016. Pebble B on the same balance has a measurement of 0.0. You'll notice they both have those zeros, 0.0 to 0. So this 0 right here is very important. It is part of the measurement, and it is part of the significance of that measurement to determine that there is a difference between those two values. You need that last 0. So this 0 right here is significant, and it's important to the measurement. Even though it's at the end and you think, I'll just leave that off. I'll just drop that off and just put it at 0.02. No, it's important, because you need to, what it's telling you is it is 0.20. It's not rounded up to 0.2. It is 0.20. It's not 0.17 and rounded up to 0.02. No, it is exactly 0.020. So you need that last 0 to make sure that you have the distinction between the two masses of the two rocks. Okay, and that can happen when you have a precise enough instrument, as you do with the superbalance. Key note there. All right, key lesson. We're going to come back to that. We're kind of building up to learning these different rules on how to determine if a 0 is significant or not. Alright, Model 3. These are types of zeros now. We're going to look at how a 0 can be used in a measurement, and then we're going to come up with some rules so that you always know whether a 0 is a significant figure or significant digit, or whether it is not. Okay? So let's look at Model 3 here, is looking at our different zeros. We have 200, which has 2 zeros in it. We've got 180, has 1 0 at the end. 140, a 0 at the end. 100 has 2 zeros at the end. Notice here we also have some zeros. They're at the beginning of the number. And here we have some zeros at the beginning and the end. Here we have them at the end. Here we have them at the end. So we need to figure out, when is a 0 significant and when is it not? Model 3 shows several of the measurements from Model 1 and Model 2. The zeros in those measurements are categorized into two types. List the two types. So either a 0 is going to just be a placeholder, meaning the 0 is just in the number so that all the other digits are in their appropriate location. Or the 0 is in a particular location because it is significant to the measurement. It is part of the precision of that instrument and needs to be there so that you know exactly what the measurement is. And I'm going to put sig fig here. Okay, that's abbreviation for significant figure. Alright, number 10 says, consider the term placeholder as it is used in the English language. Discuss 2 examples of this term in your group, or you can write them down by yourself. Summarize them here. Basically, you're just saying that it holds a place, like somebody may be a placeholder for your place in line. Hey, I got to run and get something. Please hold my place in line. Okay, and I'll be right back. You may use a placeholder to mark your spot in a book and what page are you on. All right. It simply is going to hold the place until something comes and fills that, and it's not meant to be anything more than that. It serves its purpose just by occupying that space. That's all it has to do. Describe the 2 types of placeholder zeros shown in Model 3. So in this one here, you've got placeholders, and really what it's saying is describe the 2 types or 2 locations where you are going to see placeholders. You're going to see placeholders at the end of a number. That means it could be at the end of the number, meaning in this case 200. Alright, and that would be before the decimal point. It's not written here, but you guys should know that the decimal point is always located here at the end of the number if there's no decimal point. We don't have to write it there though. So these zeros are all at the end of the number and to the left or before the decimal point. Or we have zeros that are after the decimal point. So these are going to be on the right of the decimal point, and those are the two types of zeros that you're going to see, and we have to determine whether they're significant or not. Number 12 says, if you removed a placeholder 0 from a number, would the numeric value of the number change? Yeah, it would, dramatically. So if you have the number 200, these zeros, while they're important, while they're not significant to the measurement, they're not part of the precision of the instrument, they are important because if you remove them, you would just have the number 2, which has a completely different value than 200. You need these zeros here to push the 2 into the hundreds place to give that 3-digit number its correct value. Describe the location of significant zeros in a number relative to the decimal point. So what we're doing here is any zero that is going to be to the right of the decimal point and at the end of the number is going to be significant. All the other zeros up here are just placeholders. So notice, these two zeros right here are just pushing the 2 into the hundreds place. This 0 is pushing the 1 and the 8 into their appropriate places. This 0 also is pushing the 1 and the 4. And those two zeros are pushing the 1 into the hundreds place. That's the only purpose why they're written in the number. Same thing here. This 0 and this 0 are pushing the 1 and the 6, or in this case the 2. They're pushing them into the correct location so that those other digits have the correct value. They're in the correct decimal place value. If you see a 0 and it is at the end of a number and to the right of the decimal point, it is actually part of the measurement. It is a significant figure. So in this case, this 0 that is underlined, this 0 that is underlined, that 0 that is underlined, they're all part of the precision of the measurement. You are measuring this mass out to not just the nearest unit. It's not 177. It is 177.0. You think it's exactly 177.0. Not 177.1, not 177.2. It is 177.0, and that is using an instrument that measures out to the nearest hundredth. So that 0, this 0, this 0, and this 0 are all significant. So to answer this question down here, describe the location of significant zeros in a number relative to the decimal point. They are always to the right of the decimal point. At the end of the number. Okay? 14. If you removed a significant 0 from the end of a number, would the numeric value of the number change? In this case, for example, if you had 177.0, this 0 is significant. It's part of the measurement. But if you were to remove it, you would have 177. These two, as far as the numeric value, are going to be identical. If I gave you $177.0, that's the same as $177. So the numeric value hasn't changed, doesn't change, but the precision of the measurement is different between those two those numbers. Okay, this one is measured out to the nearest hundredth of a unit. This one is measured out to the nearest unit. But dropping the zeros at the end of a number that are to the right of the decimal are not going to change the numeric value of it. Okay? Alright, placeholders are very important. They help put the decimal point in the correct spot. However, they are not significant when it comes to the certainty of a measurement. In other words, Placeholder zeros cannot be a certain or estimated digit in a measurement. Okay, remember you have numbers you're certain about, and then the last one is the estimated value. They may show up in calculations, however. For example, if you convert 29.3 meters to 29,300 millimeters, the zeros that you add to the measurement were not read from the measuring instrument, but they're there because they need to move the 293 into the correct location because you converted from one unit to another unit. Alright, little practice here. Determine if the zeros in the measurements below are significant or not. If a zero is significant, underline it. Let's look at A. 650. That zero right there is just a placeholder. It is not significant. This instrument is measuring to the nearest 10 meters. So that zero is not significant. B. 42.0. Yes, this instrument measured out to the nearest tenth of a second. This is significant, and I will underline it. Those three zeros in C are not significant. They are simply placeholders, and they are not part of the measurement, the precision of the instrument. These three zeros, however, are important in the precision of the instrument, and that is telling you that this is being measured out to the nearest thousandth of a kilogram. Yes, significant. In this case, these three zeros are not part of the precision or the significance of your measurement, and they are simply pushing the 8 into the correct location. This 8 right here is telling you that your instrument is measuring to the nearest thousandth of a milliliter. But these zeros, the purpose of them, I shouldn't underline them, sorry. These zeros right here, the purpose of them is just placeholders. They're just placeholders. Alright, these three zeros right here are placeholders, but the last one is a significant figure. Alright, I hope you're figuring out the difference between all of these. So, as I mentioned, I told you we're going to come to some rules, and here they are. Here are the 5 rules for determining whether digits in a measurement are significant or not. Match each rule to a set of examples in the table below. The significant digits in each example are underlined. So, here's rule number 1. All non-zero digits are significant. So the digits 1 to 9 are always going to be significant in your measurement, in your value. Sandwiched zeros, those that occur between two sig figs, are significant. So if you've got 109 and the 0 is in between two non-zero digits, that 0 is significant. If you've got 0.0301, this 0 right here is significant because it is between two non-zero digits. Rule number 3, zeros that are only placeholders for a digit, for a decimal, are not significant. And as I mentioned already, those at the beginning of a decimal or those at the end of a number are not going to be significant. Zeros at the end of a number that also contains a decimal point are significant. Let me just clarify. This is very, very important. There is a huge difference between 100 and 100 with a decimal at the end. If I place or you place a decimal at the end here of a number, you are explaining to your audience, to the people reading your number, that this is measured out to the nearest unit. That you think the measurement is exactly 100. You didn't round it to the nearest 100. You think it is exactly 100, 100 units, whatever the units are. So if there's a decimal point here, then these zeros are significant. Whereas if there is no decimal point, these two zeros are not significant. They're just placeholders. Okay? The last rule, exact numbers. Exact numbers just mean like you count something. I counted 10. That's an exact number. May be thought of as having an infinite number of significant digits. These include numbers that we count or are defined values. They may be values that are used in conversions, for example. There are 2.54 centimeters in an inch, something like that. So you don't have to consider, you don't have to worry about significant digits when you're working with exact numbers. All right, let's compare rule 1, 2, 3, 4, and 5 to the different sets of numbers down here and see which rule is being applied in each set. So right here we have set A. It looks like you've got zeros that are being sandwiched, is my guess, that are being sandwiched in between non-zero digits. Okay, so sandwiched zeros here are being considered as significant. So that would be set A is demonstrating that rule. Set B, they're underlining 63 and 4 and 97 and 4, but not the zeros in this case, because the zeros are just placeholders. So in this case, set B is showing you that zeros that are only placeholders are not significant. So set B is showing that to you. Set C is underlining all of them. Notice all of these are significant, except for these two zeros at the beginning, and that is because you've got zeros in between the 3 and the 4, and you've got zeros at the end. You have a 0 at the end to the right of the decimal point. So zeros at the end of a number that also contains a decimal are significant, and that would be rule 4. So that is set C that is showing you that. Set D, notice that we've got all non-zero, all non-zero, all non-zero. These are all non-zero, and in this case, this 0 should not be underlined, by the way. All right? So in this case here, set D is showing you that all non-zero numbers are significant, and that leaves us with set E. These are exact numbers. One dozen is exactly 12. 1 meter is exactly 100 centimeters. We count 29 students on the bus. Those are exact numbers. You don't have to worry about significant figures when you're working with exact numbers. So that is set E right there. All right. Let's underline number 17 in the measurement below. The significant digits are underlined. Determine the rules that were used to decide which digits were significant and which were not significant. So in this case, 4, 2, and 0. In all of these, by the way, anything that is non-zero is going to be significant. So that's one of the rules. Anything that is non-zero is going to be significant. Okay. In this case, you have a 0 that is to the right of the decimal point and at the end, and therefore that 0 is significant. Here you've got zeros that are just placeholders, not significant. Here you have a 0 to the right of the decimal point at the end. This one is significant. 0 at the end. That, by the way, students. Here's the difference. This is accounting. So they're saying you have exactly this many students. So this has an infinite number of significant figures. They're all going to be significant because you're measuring it as an exact number. You know exactly 590 students. There's no uncertainty there whatsoever. Here, all of these are going to be significant because this last 0 is significant because it is to the right of the decimal point at the end of the number, and therefore, since this is significant, then these zeros in between are going to be significant. It's sandwiched between. These two zeros are sandwiched between a significant 0 and the 5 and the 2, which are always significant. This 0 at the end is not significant because it's simply a placeholder. The 0 that's sandwiched between the 6 and the 2 is significant, so those 3 are significant right there. Number 18, we are going to underline all of the significant digits here, and as we do so, we'll just mention kind of the rule that applies. 9 and 4 are significant. Those 3 zeros are placeholders. 7, 2, but notice you're counting. Always check what the units are. In this case, you're counting something. So all 4 of these are going to be significant because it is an exact number. In this case, The 4, 3, 8, and 0 are all significant. Those zeros are simply placeholders. In this case, all of these are significant because that 0 to the right of the decimal point at the end is significant. So everything that's in between the 4 and the last 0 is also significant. These first 4 digits are significant. That last 0 is not. It's just a placeholder. And in this case, this is a conversion. Exactly 1,000 grams is 1 kilogram. So all of those are significant because it's an exact number. You are certain it is exactly 1,000, and you're not estimating any of those digits whatsoever. All right. Our extension question here deals with scientific notation. And the power in writing your number in scientific notation is that when you do so, the number of digits that you're showing in your scientific notation are all going to be significant. If you don't know about scientific notation, I'll do a quick review here. If you've got the number 3,000, that means 3 times 10 3 times. So this means 3 times 10 to the third power. If you've got 0.003, that means actually 3 divided by 10, 1, 2, 3 times. And to show division by 10, we use a negative exponent like that. So if it's a large number, you're going to move your decimal point, which in this case would be at the end. You move it until you get a number between 1 and 10, not including 10, like 1 point something, 2 point something, 8, 9 point something. You have to have a number between 1 and 10. And then if it's a large number, you're going to multiply by 10 a positive number of times. If it's a small number, again, you move the decimal point to where you have a number between 1 and 10, and then you divide by 10 a certain number of times, and you denote that by a negative exponent. In this case, when you do this, and you write this as in scientific notation, it has a numeric part and it has a power of 10 part. This numeric part right here is always going to have all of its digits are going to be significant, because by writing it in scientific notation, you eliminate all of the non-significant zeros. For example, 3 times 10 to the 4th means 30,000, but if you write out 30,000, only the 3 is significant. All those zeros are not. All those 4 zeros are taken care of by multiplying by 10 4 times. So notice that 3 right there is the only significant digits, and you write it, when you write it in scientific notation, that's the only one you write. If you have 3.00, these zeros are significant, okay? But you wouldn't know that if you expand it and write 30,000 here. You wouldn't know that these zeros are significant if you expanded it, but you would if you write it in this scientific notation, because these zeros are to the right of the decimal point. And you're telling the reader, I've measured this to the nearest hundredth of a meter. 7 times 10 to the negative third is 0.007, but 7.00 times 10 to the negative third is 0.00700. It's got 3 sig figs. Okay? So let's just use this model now to answer some of these questions. The measurements in Model 4 are written in both scientific notation and expanded notation. Copy one example for each below. All right, scientific notation is the 4.10 times 10 to the 4th, and the expanded is 41,000. Refer to the 2 measurements in set A of Model 4, right here. Do the 2 measurements have the same numeric value? Numeric value, yes, 30,000, 30,000. They both have the same numeric value. But were the 2 measurements made using the same instrument? No. This measurement right here is only one significant figure. This here is to the nearest hundredth of a meter. This second number is much more precise, using a much more exact instrument. So just be aware of that. That's the power of writing it in scientific notation, is you always will know the number of sig figs, and you can always tell how precise of an instrument you are using. Number 21, look at all the measurements in Model 4. All of these here. We're going to look at all of these measurements here. When a number in scientific notation is changed to expanded notation, are any of the added zeros significant? Give 2 examples to support your answer. So number 21. When you go from scientific notation to expanded notation, scientific notation to expanded notation, you are only adding zeros that are placeholders. You added those 3 zeros, those 3 zeros. Same thing here. You added those 3 zeros, those 3 zeros. Over here, you added those 3 zeros, and you added these 2 zeros. You added these 4 zeros, and you added those 2 zeros. None of the zeros that you add when you expand a number from scientific notation are going to be significant. None of them are. They're simply placeholders to expand the number. Okay? None are significant. Number 22. When a number in scientific notation contains a significant zero, is that zero also significant in the expanded notation? Give 2 examples to support your answer. So in this case, number 22, yes, if I write 3.00 times 10 to the 4th, and that is equal to, in expanded notation, that's equal to 30,000, but it's harder to know in expanded notation that these zeros, these 2 zeros, are significant, but they are. And so it's really misleading when you write it in expanded notation versus scientific notation. Here, scientific notation, it's obvious that you've got 3 sig figs, but here it's not. But these 3 numbers are still significant, it's just that it's hard to tell. These last 2 zeros are not, they're just placeholders. Okay? And number 23, we've got write each of the measurements below in expanded notation and underline sig figs. So if we are to expand this, this is going to be, again, it's really simple. This is going to be a large number, positive power of 10. I'm going to move this decimal point 6 places to the right to make a big number. 1, 2, 3, 4. And then I got to fill in some placeholders. 5, 6. So that's 5,078,000, and all of these numbers here are significant. Those last 2 are not. 0.72. By the way, this would not be, even though it looks like it's in scientific notation, it's not. The correct form here would be 7.200 times 10, and since I moved this over 1, this here has to come down by 1. Okay? So, these 2 are the same value. If I take 0.7200 times 10 4 times, I'm going to get 1, 2, 3, 4, 7200. Or if I take 7.200 times 10 to the 3rd, if I multiply this by 3, or 3 by 10 3 times, I get 7200. Same thing. 1, 2, 3. But this is the correct scientific notation form because this numeric number is between 1 and 10. Up here it is not. 0.7200 is not. So in this case, 7, 2, 0, and 0 are all significant figures. And 4.800 times 10 to the negative 4th, I'm going to have a very small number. I'm dividing by 10 4 times. Decimal point's going to go this way. 1, 2, and I got to fill in some zeros. 3, 4, and I got to fill in some zeros here. And that's where my decimal point's going to go. So it's going to be 0.0004800. And you can put a 0 at the front there as well. All of these zeros that I added are simply placeholders. It is the, I'll circle those, sorry. It is the last 4 that are all significant. And then 3,700 times 10 to the negative 3. Again, this is not in scientific notation. If we wanted in scientific notation, we really should write 3.7 times 10. And if I had negative 3 here, here's the decimal point. If I divide by 10 3 times, I would go 1, 2, 3. Okay? So in this case, 3.7 times 10 to the 0 power, because I'm not going to multiply by 10. I just want 3.7. So 3.7 times no zeros, or times no tens. So 10 to the 0, which is the same thing as 1. So this is just going to be 3.7, and these zeros are not significant there, but you can tell that they're not significant when you write it in scientific notation. Okay? Alright, I hope that is very helpful. It's very important to know the difference between what zeros are significant and what are not. It helps you determine the precision and how exact your measurement is, what instrument you're using, and how exact and precise your instrument is. Okay? So continue to work on that, and it will come up again and again as we look at measurements, and as we look at how to take those measurements and do some calculations with them and retain the correct number of sig figs. Alright, we'll see you in the next video.